Hey guys, my name is IBM and I welcome you to my YouTube channel. Today I would like to resolve Physics 97202 paper 2. This is October-November 2022 paper 2-3. So without wasting time, I would like to take you to the question paper. So here is the question paper. You can read through the instructions. I will not really go through the instructions. You can go through the data given. You can also go through the formula normally used. I'll go straight to question number 1. The rate of flow of a liquid along a narrow pipe of length L of radius R is given by the equation Q is equal to alpha R power 4 divided by L, where alpha is a constant. An experiment is carried out to determine the value of alpha. The data from the experiment are shown in the table. Use information in the table to show that the SI base unit of alpha is S power minus 1. Okay, so I'll first of all make alpha the subject. So alpha is going to be equal to Q times L divided by R power 4. So I have to list the units. Oh, the units have been listed. Q has been given, R has been given, M has been given. So the units of alpha will be for Q, which is M power 3 S power minus 1 times L, which is M divided by R power 4, which is M power 4. And when we simplify this, this becomes M power 4 S power minus 1 divided by M power 4, and this one cancels. So this gives us S power minus 1. Show that the percentage uncertainty in alpha is 15%. So using that equation, because we have multiplication, division, power, I'll just add the percentage uncertainty. So percentage uncertainty in alpha should be equal to percentage uncertainty in Q plus percentage uncertainty in L plus 4 times percentage uncertainty in R. So if I substitute the quantities given here, this would be 3% plus L, which is 4%, plus R, which is 4 times 2. I multiply R by the percentage of R by 4 because R is raised to power 4. So this is 37 plus 8, which is 15%. Then calculate alpha with its absolute uncertainty. Give your answer to an appropriate number of significant figures. Okay, so if I have all the quantities in SI units, I'll just substitute alpha. Alpha is going to be equal to QL over R power 4, which is the same as Q is 2.72 times 10 to the power of minus 8. 2.72 times 10 to the power of minus 8. And then L is 2.5 power minus 2. 2.5 times 10 to the power of minus 2 divided by R, which is 7.1 exponent minus 5. So this is 7.1 times 10 to the power of minus 5, and this is going to be power 4. Then I'll just check my calculator. 2.72 exponent minus 8 times 2.5 exponent minus 2 divided by 7.1 exponent minus 5, and this is raised to power I'll raise this to power 4. So this is giving me 2.676. 2.676 times 10 to the power of 367 to the power of 7. 2.668. Okay. It's always good to have many significant figures here so that when you write the final answer, because the absolute uncertainty will determine the number of significant figures you write the final answer. So I'll find the absolute uncertainty in alpha to be equal to the percentage, which is 15, divided by 100, then times my value of alpha, which is 2.68, times 10 to the power of 7. So I'll just simply say I'll multiply this answer by 0.15. So this is giving me 4.0 times 10 to the power of 6 times 10 to the power of 6. Now I must write this answer to the same power of 10 as the true value. So I must move another step to the left hand side so that it becomes 0.4 times 10 to the power of 7, because they should have the same power, which is power 7. So this is one, of course, writing the absolute uncertainty to one significant figure, it is going to be one decimal place. So the absolute uncertainty is going to be 0.4. So since the absolute uncertainty is to one decimal place, then the true value should be rounded off to one decimal place. So this will be 2.7. So that will be my answer, 2.7 plus or minus 0.4 times 10 to the power of 7. The engine of a toy rocket pushes gases vertically downwards, and this results in the rocket accelerating vertically upwards from the ground. The rocket starts to move from rest at time t equals 0. The variation with time t of the vertical velocity v of the rocket from the first 3 seconds for the first 3 seconds of the flight is shown. As the rocket moves, the thrust force T provided by the rocket engine is 16 newtons. So T is 16 newtons. Assume that the mass of the rocket is constant for this part of its flight. Assume that air resistance is negligible, so the equations of motion can apply because the acceleration will be constant. For this part of the rocket's flight, show that the acceleration of the rocket is 55 meters per second. Because this is a straight line, the acceleration is going to be simply the gradient. So I'll just look for the gradient. The scale on the vertical is 5 over 10, which is 0.5. So this is 16.5. That is 16.5. So the acceleration is equal to the gradient, which is going to be 16.5 minus 0 divided by 0.30 minus 0. I'll just check with my calculator. 16.5 divided by 0.3. So that is 55. Then state an expression for the resultant force F experienced by the rocket in terms of the thrust force T and the weight. So the rocket is moving upwards, the thrust force is upwards, T, the weight is vertically downwards, and it is accelerating upwards. So the resultant force, state an expression for the resultant force F experienced by the rocket in terms of the thrust force T and the weight W of the rocket. So as the rocket moves, the thrust force T provided by the rocket engine is 16 newtons. Assume that the mass of the rocket is constant for this part of its flight. Assume that air resistance is negligible. For this part of the rocket's flight, show that the acceleration of the rocket is 55 meters per second. Okay, so assuming the weight is downwards and the thrust force is upwards, so it means I would say the resultant force F could be the weight minus the tension. The resultant force is going to be the weight minus the tension, because the weight is downwards and the thrust is upwards and the weight is downwards. So the resultant force is the difference between these two forces. Then calculate the mass of the rocket. So for the mass of the rocket, since I have the resultant force, and the resultant force is mass times acceleration, since I have the acceleration and the resultant force is mass times acceleration, then I will be able to predict the mass of the rocket. So resultant force F is equal to M times A. And resultant force, remember, was the weight minus the thrust. But since motion is upwards, I will do it the other way around. I would rather say resultant force F is equal to the thrust minus the tension, but any of these would be correct. So I'll leave out this one and I will take this one because motion is upwards. So let the resultant force be the thrust upwards minus, so F should be the thrust upwards minus the weight downwards. So the thrust upwards, the resultant force is MA, which is equal to the thrust T minus mg. So when I collect like terms, it means that acceleration, m into A plus g is going to be equal to the thrust. So in other words, the mass is going to be the thrust divided by A plus g. So the mass of the rocket is going to be 16 divided by the acceleration, which is 55, plus g, which is 9.81. So I have 16 divided by 55 plus 9.81. So this is giving you 0.24, 0.25. Okay. Then at time t equals to 0.30, a small piece of metal separates from the rocket. Calculate the height of the rocket above the ground at t equals to 0.30 seconds. So if a small rock separates from the rocket, remember it was initially moving at a speed of 16.5 meters per second. So let's say it is here, initially moving. Hope I didn't change this question. Okay. So it was initially moving upwards. But calculate the height of the rocket above the ground at t equals to 0.3 seconds. So they said a small piece of metal separates from the rocket. So if it separates from the rocket, it means its initial speed is going to be 16.5 meters per second. Its initial speed, if it separates from the rocket, its initial speed is 16.5 meters per second. So it may maybe go up vertically upwards, but we want to calculate the height of the rocket above the ground at t equals to 0.5 seconds. So using S equals to ut plus a half at squared. So initially it started with the velocity 0 before time t at t equals to 0, the velocity was initially 0. So it means I'll simply say S equals to a half times the acceleration upwards is 55, then times t, which is 0.30 seconds. So this gives us 0.5 times 55 times 0.3 squared, which gives us 2 point, I think this is approximately 2.5 meters. So at that time when the small piece of metal separates from the rocket, then it is at a height of 2.5 meters. Alternatively, I could use the distance S to be the area under the graph. And it is a triangle, so it is a half times the base, which is 0.3, times the height, which was 16.5. I think it gives you the same answer, area under the graph. Or you could also use another equation, which is S equals to a half into U plus V, then times T. This is another method. This is another method. If I use this, it will be a half. It started from rest, so initial velocity is 0, final is 16.5, and the time is 0.3, so it gives you the same answer. You could also use v squared equals to u squared. I'll also use v squared equals to u squared plus 2as. Okay, which means final velocity is 16.5, that is after 0.3 seconds squared, equals to, started from 0. It was moving against gravity, so I'll say minus 2 times 16 squared equals to 0.2 squared, 0 squared minus 2 times 9, no, the acceleration is 55. So the acceleration, I will just take it positive because it's 55, then times s, which is going to be the height h. So let me check this. 16.5 squared divided by 2 times 55. So this gives us h as 2.5 meters. So I could use this, but remember the acceleration is positive, it is not negative. So it is, because I'm not using g, so it is 55 times h. Okay, so this next part is the most important one. The speed of at which capture the speed at which the piece of metal strikes the ground. So remember, a small piece of metal separates from the rocket. So I need it to find its initial. If it separates from the ground from the rocket, its initial speed is 16.5. Then I would use maybe v squared equals to u squared plus 2as. So what is the initial speed when it just separates from? If this is it is on the rock. I mean, it is on the rocket. A small piece is on the rocket. That means its initial speed is the speed of the rocket at that time at 0.3 seconds. So the initial speed must be 16.5 meters per second, because the rocket was moving at that speed when the piece of metal separates from it. Then if the initial speed is 16.5, we want to find the final speed. So I'll simply say v squared is equal to 16.5 squared plus, because now it has separated from the rocket, then it means its acceleration is going to simply be acceleration due to its mass, which is acceleration due to gravity, no longer 55 meters per second, because it will only be moving under the influence of its gravity. So the only option we have, if it separates from that, it means it's going to fall downwards. So it is going to be 16.5 squared plus 2 times 9.81, then times g, which is, times the height it will fall through, which is 2.5 meters. So I'll just get the calculator. 16.5 squared plus 2 times 9.81 times 2.5. So this is, I'll get the square root of the answer, which is 17.9. So v is equal to 17.9. So this is going to be the speed, 17.9. State the principle of moments. So we know that for a body for an object in equilibrium, the sum of clockwise moments is equal to the sum of anti-clockwise moments about the same point. So for an object to be in equilibrium, the sum of clockwise moments should be equal to the sum of anti-clockwise moments about the same point. First of all, you should be referring to equilibrium. Second, you must mention sum, and third, you must mention about the same point. That is if you are stating the principle of moments. A whole plastic sphere is attached at one end of a bar. The sphere is partially submerged in water and the bar is attached to a fixed vertical support by a pivot P, as shown in the figure. The sphere has a weight 0.3 newtons. The distance from P to the center of gravity of the sphere is 0.29 meters. Assume that the weight of the bar is negligible. The weight is negligible. Calculate the moment of the weight of the sphere about P. So the weight of the sphere should be acting vertically downwards, and its weight is 0.30 newtons. So we need a perpendicular distance from the pivot. So this is a perpendicular distance from the pivot. And if you use this angle here, of course, it is 40 degrees. This side is going to be the adjacent. This is opposite, so this is hypotenuse. So it means cos of 40 is equal to the adjacent divided by the hypotenuse, which is 0.29 meters. So it means the perpendicular distance, which is the adjacent, is 0.29 cos of 40. Okay, so moment is remember moment is force times perpendicular distance. This is force times perpendicular distance from the pivot. So the moment or the torque is going to be 0.30 times the perpendicular distance, which is 0.29 cos of 40. Okay, so 0.3 times 0.29 cos of 40. So this is 0.666. So 0.066. Or I can just write 0.067 Newton meters. The system shown in the figure is part of a mechanism that controls the amount of water in a tank. Water enters the tank and causes the sphere to raise. This results in the bar becoming horizontal. The figure shows the system in its new position. Remember, the weight of the sphere has not changed. It is still 0.3 newtons. But there's another force which is acting on the sphere, which is of course going to be the upthrust. In this position, the rod R exerts a force to compress the horizontal spring that controls the water supply to the tank. R is positioned at a perpendicular distance of 0.017 meters above P. Okay, so R is positioned at a perpendicular distance, so it means the tension here, its perpendicular distance is going to be 0.017 meters. So there's a force here from the spring, which is the tension. The variation of the force F applied to the spring with the compression X of the spring is shown in the figure. Okay, I can first know what this is. The scale is 5 divided by 10, which is 0.5. So this is most likely going to be 21. Use the figure to calculate the spring constant. So of course, by Hooke's law, K is the change in F over the change in extension, which is the same as the gradient. So K is going to be 21 minus 0 newtons divided by, on the x-axis, we have 10 minus 0, but this is in millimeters. So I will say 10 minus 0 times 10 to the power of minus 3. So this is 21 divided by 10 to the power of minus 3. So which is 21 divided by 10 exponent minus 3, which is 2100 newtons per meter. At the position shown in the figure 3.2, the system is stationary and in equilibrium. The radius of the sphere is 0.048 and 26% of the volume of the sphere is submerged. 26% of the volume of the sphere is submerged. 26% is 0.26 of the volume of the sphere which is submerged. The density of water is 1000 kilograms per meters cubed. Show that the upthrust on the sphere is 1.18 newtons. So the volume of the sphere, we know that the volume of a sphere is 4 over 3 pi r cubed, which would be, let's say this is 4 pi over 3 times 0.0480 cubed. That is the volume of the sphere. And we know that the upthrust is equal to the weight of the fluid displaced, or the upthrust is the weight, which is mg, which is going to be density times volume, then times g. So the upthrust force is going to be the density of the liquid the sphere displaces, which is 1000 times g, which is 9.81, times the volume of the sphere, which is going to be 4 pi. By the way, this is the total volume of the sphere, but the volume which it displaces is going, remember, this V is the volume which is displaced, volume displaced. So this is going to be 4 pi over 3 times 0.0480, but this is the total volume of the sphere. But we want, to get the upthrust, we need the volume of the sphere displaced, because this is the mass, the weight of the sphere. The upthrust is equal to the weight of the fluid which is displaced. This is weight displaced. So we have to consider the volume displaced, which is going to be 0.26 of the total volume. So this will be multiplied by 0.26. So I have 1000 times 9.81 times 0.26 times 4 pi times 0.048 divided by 3. So this is 5. Oh, I didn't raise this to power 3. So I'll just multiply again times 0. Answer times, I have to raise that to power 3, so I will multiply again by 0.048 squared. 0.048 squared. So this gives me 1.18 newtons, because this is supposed to be raised to power 3. By taking moments about P, determine the force exerted on the spring by the rod R. So if we consider that there is equilibrium here, the forces acting, like I mentioned, we have the upthrust force upwards, the weight of the sphere downwards, and there is this one here. So this is causing anticlockwise moments. This is causing anticlockwise moments, and the upthrust is causing clockwise moments about the point P. So taking moments about that point, let me check the perpendicular distance. This is 0.29 for the weight of the sphere. It's also 0.29 for the upthrust, but it will be 0.017 for the tension. Okay. So by taking moments about P, determine the force exerted on the spring by the rod R. So the force exerted by the spring is going to be F times the perpendicular distance from where we're taking moments, which is 0.017. That was clockwise, plus the weight of the sphere was 0.30. Its perpendicular distance from the pivot was 0.29. These are clockwise moments. This should be equal to anticlockwise moments, where the upthrust is anticlockwise 1.18 and its perpendicular distance is 0.29. So from my calculator, I have 1.18 times 0.29 minus 0.3 times 0.29. Then I divide this by 0.017. So this is giving me 15.0. So this is 15.0 newtons. Okay, so F is 15.0 newtons. Calculate the elastic potential energy EP of the spring. Of course, for elastic potential energy, it is a half kx squared. Elastic potential energy is equal to a half kx squared, which is a half. We already got the k was 2100, and the x is, let's see, what is x? The force is 15. 15 is corresponding to, no, I'll just find the x from the formula. From F equals to kx, it means x is going to be F over k, and F is 15, that is the force in the spring, and the constant is 2100. I'll just use this. So I'll say 15 over 2100, but this should be squared. So this is to help me find the extension. So I'll just take my calculator, 0.5 for a half times 2100 times 15 squared divided by 2100 squared. So this is giving 0.054 joules. When the sphere moves from position shown in the figure to the position shown, that is from figure 3.1 to 3.2, the upthrust on the sphere does work. Assume that resistive forces are negligible. Explain why the work done by the sphere is not equal to the gain in elastic potential energy of the spring. So they say the upthrust does work. Of course, the work done by the upthrust, is doing two things. Number one, the sphere is raising, so it is equal to the gain in gravitational potential energy. Number two, it is increasing the elastic potential, it is stretching, it is compressing the spring, so it is plus elastic potential energy of the spring. So explain why the work done by the upthrust is not equal to the gain in elastic potential energy. Because the sphere raises in height, it means it gains gravitational potential energy. So I'll simply say the sphere has gained gravitational potential energy. The sphere has gained gravitational potential energy. So the work done by the upthrust is equal to gain in gravitational potential energy plus gain in elastic potential energy. Okay, so this is the main point. That's why I'm writing these ones in short, but you can write these in full. Gain in gravitational potential energy plus gain in elastic potential energy. Question number 4, I think this is waves. A progressive longitudinal wave travels through a medium from left to right. It's from left to right. The figure shows the positions of some of the particles of the medium at time t equals 0, and a graph showing the displacement at the same time t naught. Particle displacements to the right of their equilibrium positions are shown as positive on the graph, and particle displacements to the left are shown as negative on the graph. The period of the wave is t. So the period of the wave is t. On the figure, draw circles around two particles which are exactly one wavelength apart. Because this is a displacement against distance, so one wavelength apart. So you can, one wavelength apart, I could consider this particle here with this one. Those ones are one wavelength apart. I could also consider them, use a different color for different particles. I'll consider this particle here with this particle here. They are one wavelength apart. I will use a different color for another pair. I would also just consider, you could consider this particle here with, but this is at the peak. This is not exact at the peak, but I think this particle here is one wavelength apart with this one, but the most appropriate one, X, the particle at X here and this one here, or I can consider the particle at Y with the first one, or I can consider the particle here with the particle here. Those are exactly one wavelength apart. So, but X, this one and this one are the best, I think. That's one wavelength apart. On the figure, sketch the line on the graph to represent the displacement of the particles for the longitudinal wave at time t plus a quarter cycle. Of course, if at a quarter, at t naught, we have maximum displacement, particles are at their maximum displacement in that direction, then of course, again, at a quarter a cycle, the particles are going to vibrate towards the right to form the next compression. So at t equals t naught, so particles vibrate to the right to form the next compression. That means the graph is going to be just the mirror image of this one here. So particles vibrate towards the right to form the next compression. To form the next compression. And if we form the next compression where particles, where particles are under maximum pressure, then we must have a graph which is going to be just the mirror image of this. Because remember, at t equals to t naught plus a quarter cycle, it means the particles in one section, particles in one section, okay, particles in one section are going to move towards the right hand side, or the particles in this section here are going to be moving towards the right hand side in a quarter a cycle. Therefore, they will compress at the next point to form an interference pattern, which is basically going to be, or to form a compression, which is going to be a point where the displacement is zero. If you want to look at it by looking at phase difference, phi is going to be equal to 2 pi into a quarter of a cycle. This is a quarter cycle minus negative a quarter of a cycle. So it means two corresponding particles will move apart by half a cycle. So if I divide this by the period, this gives me pi, I think. A quarter plus a quarter, because it's minus minus. So it's a quarter plus a quarter, which is a half. And this gives me pi. That means for the next a quarter a cycle again, we shall have points of zero displacement, but this time it will be a reversed graph. So this is going to be a curve of this nature. Okay, so two corresponding particles will therefore form, they will still undergo maximum displacement, or they will still form a displacement pattern which is a mirror image of just this one after a quarter cycle. Then if it was t naught plus t over 2, that is plus a half a cycle, then we'll just have the particles will just form a horizontal line. State the direction of the motion of the particle z at t naught plus t. Of course, we have already said that the particles are going to be moving towards the right hand side to form the next compression, so the particle z must be moving towards the right hand side. So this is simply to the right. Okay, then the frequency of the wave in A is 16 kilohertz. The distance between particles x and y is 0.19 meters. X and y. Do you notice that x and y is this is half of a wavelength? So half a wavelength is 0.19. So I'll say half of a wavelength is 0.19 meters. So which means the wavelength is going to be twice. 2 times 0.19 meters. And I think this is 0.38 meters. Calculate the speed of the wave as it travels through the medium. So from v equals lambda times f, v is going to be 0.38 times f, which is 16,000. So 0.38 times 16,000. So that is 6080 meters per second. A longitudinal sound wave is traveling through a solid. The initial intensity of the wave is I naught. The frequency of the wave remains constant and the amplitude falls to half. So the amplitude A is going to be a half of A naught. Let the amplitude of the first one be A naught. Determine in terms of I naught the final intensity of the wave. Okay, so I'll just use two equations here. Remember, intensity is directly proportional to amplitude squared. For the first one, I naught is equal to a constant times A naught squared. For the second one, I is going to be equal to K, where there is amplitude, I'll put A naught over 2, and this is squared. So it means I'll just simplify this. So I is going to be equal to K A naught squared divided by 4. So this is going to be equal to a quarter, where there's K A naught squared, I will put there I naught. So the answer here is going to be a quarter I naught, or 0.25. So this is 0.25. The sound wave in C now meets another sound wave traveling in the opposite direction. State a condition necessary for these two waves to form a stationary wave. So traveling in opposite directions, we have seen the sound wave in C, which has amplitude half of A naught, meets another sound wave traveling in opposite direction. State the condition for these two waves to form a stationary wave. If they're already traveling in the opposite direction, then it means they should have the same frequency or period, or the same wavelength. For stationary wave to be formed, the wave should be of the same kind, same type, traveling in opposite direction, same frequency, same period, same wavelength, and they should meet at a point. State two ways in which a stationary wave differs from a progressive wave. Okay, there are several ways in which a stationary wave differs from a progressive wave. The simplest is a stationary wave has nodes and antinodes, and a progressive wave does not. So a stationary wave has nodes and antinodes. progressive wave does not. That's number one. Number two, I think a stationary wave does not transfer energy. A progressive wave does. A stationary wave does not transfer energy. A progressive wave does. Those are two. The number three, I'm not following the lines given here, so I want to write more. You remember from your class that two adjacent particles in a stationary wave vibrate in phase, which is not the case with the progressive wave. So stationary waves have a stationary wave, I will just say one, a stationary wave has adjacent particles that are in phase. Adjacent particles in a progressive wave are out of phase. Okay, then the other one is you can talk about the different points on a stationary wave which have different amplitudes. Yet for progressive wave, all particles will reach the same maximum displacement. So I'll say different points on a stationary wave have different amplitudes. And all points on a progressive wave all points on a progressive wave have the same amplitude. So these are the common differences between a stationary wave and a progressive wave that I expect a science student to be able to state. Electricity state Kirchhoff's second law. Remember, the second law is about EMFs, conservation of energy, EMF and PDs. So you could say around a closed loop or a closed circuit, the sum of EMFs is equal to the sum of PDs. Those are already 2 marks. Alternatively, some of my students prefer to say the algebraic sum of EMFs and PDs is 0 around a closed circuit. Algebraic sum of EMFs and PDs is 0 around a closed circuit. Algebraic means you are giving these current sign, EMF signs, either positive or negative, and when you sum up, you should be able to get 0 if it is a closed circuit. Three identical cells, each of EMF 1.5 volts and internal resistance 590 milliohms are connected in parallel across a conductor as shown here. Okay, so of course we know that the total EMF across the conductor must be the EMF of just one cell. So the effective, if your cells are in parallel, the effective EMF, if cells are in parallel, the effective EMF is the EMF of just one cell. So that means the effective EMF across the conductor is the EMF of just one cell. But remember, the current here is a combination of all the currents through all these cells. If they're identical, that means the current through all of them is going to be the same. So let this be internal resistance R. The current here will be I1, I2, I3, but these currents are going to be identical. So the conductor is composed of two cylindrical sections, A and B. The total resistance of the circuit is 2.2 ohms, total resistance. Okay. Show that the resistance of the conductor is 2 milliohms. Let's find the total effective resistance, internal resistance of these cells. So using 1 over R total is equal to 1 over each of them. So it will be 1 over 0. It was 590, which is 0.959, plus 1 over 0.59 plus 1 over 0.59. So I'll say 1 over R total is going to be equal to 3 over 0.59, which implies that total internal resistance is going to be 0.59 divided by 3, which is going to be 0.59 divided by 3, 0.197. That's total internal resistance. Then that total internal resistance should be added to the resistance of the conductor. Let's say it is R. So it means 2.2 should be equal to R plus 0.197. So what is R? 2.2 minus 0.197. So I'll just say, what is this? So I'll just say R is equal to 2 minus the answer, which is 1.8. So I said 2.2 minus 0.197. That is 2.0. So R is going to be 2.0 ohms as required. Then calculate the current in the conductor. Oh, by the way, I would also first find the total current in the conductor instead. I think this is also an easier method. I would find total current in the conductor. That is, total current is equal to the EMF, effective EMF, over total resistance. So effective EMF, I said, is the EMF of one cell. Total resistance is 2.2. So the current in the conductor, total current in the conductor is going to be 1.5 divided by 2.2. So the current which comes to the conductor is 0.68 ohms. And remember the current, if I consider the current in the internal resistance, current in internal resistance, I, is because the currents add up to form 0.68. So if this is I, so it is going to be just divide this by 3. So I would divide this by 3. So it will be 0.68 divided by 3. That is the current in the internal resistance of each cell. And you recall that EMF is going to be equal to the terminal PD plus the lost volts. So the EMF is 1.5. Remember, the effective EMF is 1.5. Then the terminal PD will be equal to the current, which is 0.68 times the resistance of the conductor. The lost volts. The lost volts is going to be, of course, is going to be the lost volts is just one cell. If I use Kirchhoff's law here only, you could use Kirchhoff's law here if you want. You know the current I, you know the small resistance R, and you know the current 0.68 is coming to this. So the EMF there, sum of the EMF is 1.5 equals terminal PD, which is 0.68 times R plus the lost volts, which is going to be I times 0.59. So it means 1.5 is equal to 0.68 R plus I, which is 0.68 over 3 times 0.59. So this is what I'm doing here. So this is going to be 0.68 divided by 3, that is the current, times internal resistance, which is 0.59. I'm very certain this should give us the same answer, 2.0 ohms, but that's a long way. Then calculate the current in the conductor. Okay, I think I've already calculated this current, but I will still repeat it here. So current is equal to the EMF divided by total resistance, because all the total current goes through the conductor. So this is 1.5 divided by total resistance, which is 2.2. And I think we had already calculated this above here. It was 0.68. It was 0.68. There could be another alternative. I could use concepts of PD across the cell to be equal to the PD across the conductor, because they're in parallel. So I'll say PD across one cell is equal to the PD across the conductor. So the PD across one cell is going to be, I think it is the EMF, which is 1.5, minus the PD across the internal resistance, which is 0.59 times the current in the internal resistance, which is going to be, it is the PD across the loss, it's going to be the PD across the internal resistance times the small current through the internal resistance, which is I. It should be called the PD across the conductor, which is going to be, of course, the current here is going to be 3 times the current through each of those. So this is going to be 3 times I. So this is going to be 3 times I, because the current sums up. Then times the resistance, which we have already found to be 2.0? Yes. So I have to find the small I. So the small I is going to be equal to, I'll just call it like terms. I'll say 6 minus or plus 0.59. So this is 1.5 divided by 6.9, 6.59. So I'll say 1.5 divided by the answer. So the small current is going to be 0.228 amperes. That is the small current in the cell. So remember, the current through the conductor is 3 times. So current in a conductor is going to be 3 times 0.228, which I think it gives us that answer there. Okay, I think that is a good method. You could also use a method of, I think that is fine. You can use PD across one cell is the same as PD across the conductor. So if small I is the current in one cell, and you notice that there are 3 cells, it means total current which is in the conductor is 3 times the current of just one. Then the two cylindrical sections A and B of the conductor in the figure are made from the same material. That means they have the same resistivity, they have the same length. So same resistivity, same length. The diameter of section A is 4.3 millimeters. The diameter of section B is 7.6 millimeters. The resistance of section A is RA and the resistance of section B is RB. Calculate the ratio RA over RB. So we know that area is pi d squared divided by 4. That one we know it. And we know that resistance is equal to rho L over area. So resistance would be 4 rho L over pi d squared. Remember, rho and L are the same. So I'll find R for A will be 4 rho L over pi. The diameter for A is 4.3 and this is squared. If I try R for B, it will be 4 rho L over pi. Diameter for B is 7.6 and this is squared. Then I will divide to find the ratio. RA over RB would be equal to 4 rho L over pi cancels out. 7.6 goes up, so it becomes 7.6 squared divided by 4.3 squared. Okay, so if I check my calculator, 7.6 squared divided by 4.3 squared. So this gives me 3.1. So this is 3.1. Then calculate the ratio average drift speed of free electrons in section A over average drift speed of free electrons in section B. So, of course, we know that current equals to N A V Q. So the current in section A should be, of course, the number density is constant. The charge of each charge carrier is constant. What is changing is the area. This is, of course, this will be N pi d squared over 4 times V times Q. So this is going to be times V of A times pi, where there is diameter for A, I'll put there 4.3 squared divided by 4. Then I for B is going to be equal to NQV for B times pi 7.6 squared divided by 4. Remember, the two sections are in series, so IA is the same as IB. So I'll just equate the two. And when I equate the two, NQ cancels out. So I'll just have VA times pi over 4 times 4.3 squared is equal to VB times pi over 4 times 7.6 squared. So pi over 4 has cancelled out. So VA divided by VB is equal to 7.6 squared divided by 4.3 squared. So we are still getting, I think it's the same answer from above, which is 3.1. So the answer here is going to be 3.1. The section of the figure is altered by removing one of the cells. So we remain with the two cells. State and explain the effect, if any, of this change on the potential difference across the conductor. So they have removed one cell, which means total internal resistance of the cells is going to be greater, because having more cells in parallel, having more internal resistances in parallel means total internal resistance is less. So removing one means total combined resistance is greater. Total combined internal resistance. Total combined internal resistance of the cells will be greater. That's number one. So that is because a parallel resistance has been removed, because a parallel resistance is removed. So when you remove a resistance in power, you increase total combined resistance. Okay, that's number one. These are 3 marks. So number 2, if the total internal resistance has been increased because the power resistance has been removed, so it means the internal resistance is going to take a greater share of the total PD. Because if the total internal resistance is greater, it means the internal resistance takes a greater share of the available total EMF or the available total PD, which means a smaller share goes to the external resistance. So it means the internal resistance. So internal resistance takes a greater share of the total PD. So the conductor gets a smaller share. The conductor gets a smaller share of the total PD, which means there are more lost volts inside each cell of the total PD, which means more lost volts inside each cell. There will be more lost volts inside each cell. And if there are more lost volts inside each cell, it means the PD across the conductor decreases. So the PD across. So the PD across the conductor decreases. The PD across the conductor decreases. You can still verify this by calculation. If you consider one conductor here, if you consider there are 2 now cells, it means the PD across each cell is now going to be 1.5 minus 0.59 times the current in each cell, and the PD across the PD across the conductor is going to be, this time it is going to be twice I times the resistance of the conductor R, but note that the total current or the total combined internal resistance of the cells is now greater. And if the total combined resistance of the cells is now greater, it means most like the current through each of the cells is going to be, less, and it implies that the current through the external conductor is also going to be smaller. So precisely the PD across the external conductor is going to go down. So we are saying the PD across the conductor is most likely going to decrease because the internal resistance takes a greater share of the total PD. Because it's now a greater internal resistance, it implies that the conductor will get a smaller share of the available PD, which means there is more lost volts inside each cell, which means the PD across the external conductor is automatically going to decrease. I would verify this by calculation, but I want to use the 5 minutes to finish the paper. The nuclide carbon-14 is unstable and undergoes beta minus decay, emitting a high energy electron and an antineutrino to form a new nuclide X. The equation for this decay is shown. So this is 0, -1. Complete the equation. So 0, -1. Of course, phi balance. So this should be 7. So that 7 plus -1 is equal to 6. And this remains 14. State the equation for beta minus decay in terms of the fundamental particle involved. So beta minus, we know that for beta minus, it is a neutron which changes into a proton. So if a neutron changes into a proton, we have up, down, down, changing to up, up, down. So I'll either write up, down, down, changing to up, up, down, plus. This will give us E minus plus, of course, the antineutrino that we have seen above. So that would be the equation. So in other words, we would simply say down quark changes to up quark, plus a lepton plus a neutrino. These are all fundamental particles plus the antineutrino. So this will be the equation, either that or this one here. Use your equation from Roman 1 to show how charge is conserved in beta minus decay. So let's try to check the charge on the left hand side. The charge on the left hand side is going to be equal to, we have up, down, down. So it is negative, okay, it is positive 2 over 3e plus negative 1 over 3e plus negative 1 over 3e, which gives us up, down, down. So this gives us 0. That is it 0? Positive, it is up, down, down on the left hand side. Okay, negative, okay, that is fine. Then on the right hand side, the charge on the right hand side is going to be, of course, we have up, up, down, so that is 2 over 3e plus 2 over 3e. Then down is minus 1 over 3e, then plus e, which is, it is an electron, so it is negative e, then plus 0 for the neutrino, I mean the antineutrino. This should give us, this is 4 over 3e minus 1 over 3e, which gives us 2. Okay, this is over 1. Over 1. LCM here is 3. So 2e plus 2e minus e minus 3e, which gives me 0, I think, because it is 4e minus 4e over that, which is 0. So that means charge is conserved. Or I would look at the down quark, which is negative. I would say left hand side is negative 1 over 3e. Then I will say right hand side is up quark, which is 2 over 3e, plus the electron, which is plus negative e, then plus 0, which gives me still negative 1 over 3e. So I either use the first method or the second method, and I'll just conclude hence conserved. Hence conserved. I either use the full formula, the full expression using the first equation, or I use the second equation for the second part, and the charge is the same, so it means it's conserved. Neutrinos were first proposed to exist more than 20 years before they were directly detected in order to explain a particular experiment observation about beta decay. State an observation about beta decay that is explained by the existence of neutrinos. Of course, neutrinos explain the existence of a continuous range of kinetic energies. So beta particles emitted from the nucleus have a continuous range of kinetic energies. So just how the existence of neutrinos explains the observation in C Roman 1. Existence of neutrinos. Of course, we expect that these neutrinos must take some of the energies, must share part of the energy. So the emitted neutrinos the emitted neutrinos take varying amount of energies, take varying amounts of the same total energy released in the decay. Okay, so I think that marks the end of this paper. In case there's something I didn't make clear, you can always raise your concerns. You can always give a negative comment, I don't care. Until next time, bye bye.